as mentioned, I want to talk about the Borel monadic theory of order of the reals. First, I want to give a bit of context and talk about what the decidability of monadic theories in general, and then why we need, in particular, why we need to go to Borel sets here. It turns out that actually the main feature of Borel sets we use is the Baire property, so I will expand on this and also talk a bit about the proof, and if time permits, also discuss some related questions. Okay, so first of all, I guess most of you know this, but let's shortly repeat what monadic logic is. So in first order logic, we are allowed to quantify over elements of the universe, and in second order logic, we are quantifying over elements and arbitrary n-ary relations of the universe. Monadic second order logic sits in between. We are allowed to quantify over unary relation symbols. So this, with respect to decidability, it's more problematic to get decidability than for first order structures, but easier to get it for second order structures. So maybe let's look at the most natural structure first, the natural number. There it's classically known that for first order theory, while full arithmetic is undecidable by the completeness theorem, essentially, there are many decidable fragments, the most powerful being Pressburger arithmetic, that we also spoke about. And the smaller fragments are even less expressive if one only restricts to order, which can be defined from addition, or to a successor, which can be defined from order, but out. In monadic logic, those theories become more expressive. In particular, the monadic theories of order and successor coincide by a relatively easy argument. And they are actually already more expressive than Pressburger arithmetic in some sense. But if one would try to do algebra in monadic logic and talk about the addition, for example, over the natural numbers, this would allow to define multiplication and thus actually get access to full second order arithmetic, make all of this undecidable. And yeah, in second order arithmetic, everything is completely hopeless. Even from the successor function, one can simulate the usual recursive definitions of addition and multiplication. So if we want to do decidability on monadic logic, we should somehow focus on theories of order and not on algebraic theories. If one wants to do algebra using monadic logic, this can be done by doing some restricted class of monadic logic. For example, also Urey investigated order decreasing groups using multiplication over convex subgroups. Or one can talk about Boolean algebras, countable Boolean algebras and multiplication over ideals, but for general subsets, algebra just not feasible anymore. So we should restrict to monadic theories of order. So as I mentioned, the theory of order, which I mentioned is more expressive than even Pressburger arithmetic, is usually described by omega automata, so automata operating on infinite words, and it is an always theorem of Büchi that is using these statistics decidable. The monadic theory of the rationals with order is even more expressive. It could actually be described as the monadic theory of all countable total orders, but it can also be shown decidable, for example, using tree automata of Rabin, or also the technique I will be using here. But the monadic theory of the real with order is undecidable. This is a result of Urewicz and Schiller. It turns out that it actually codes third order arithmetic in a forcing extension of the universe given by a Cohen real. And this is quite close to the precise bound, although the precise bounds are not known. The idea of the proof is to use a well-ordering of the reals. And using this well-ordering of the reals, one can define parameter set, can define a parameter set, and then code natural numbers by certain Cantor sets. But only can code them locally with the greater forcing. Maybe also some elementary facts about this. It can be relatively easily shown that the monadic theory of order of the reals is the same as the lexicographic order of either the natural, either the Baire space or the Cantor set. And it can also be seen that over the reals, the monadic theory of order is equivalent to the theory of topology, where one also can quantify over subsets, but instead of asking whether 2 points are, instead of comparing points, one can ask whether a given subset is open. This is clearly interpretable in the monadic theory of order, since the order topology is a monadic definition, but it can also be essentially reversed, since using the theory of topology, one can define intervals and thus almost cover order. So the natural question, seeing the undecidability of the monadic theory of the reals, is whether this can be, whether we can have some intermediate theory between the rationals and the reals, which is still decidable. And the candidate with decidability I've proven is the theory where quantification is restricted to Borel subsets, which prevents us from using a well-ordering of the reals to define those parameter sets, and thus at least Chela's proof from working. Certain fragments of this were already known. Using tree automata of Rabin showed that the monadic theory of the reals with strict quantification to F sigma sets, the second level of the Borel hierarchy, is decidable. And actually, it turns out that this is quite close to the general monadic theory of Borel sets, namely if one restricts to Boolean combination of F sigma sets. I could show that this forms an elemental substructure of the Borel set. And we get also many intermediate theories which are equivalent. For example, if one takes any intermediate level of the Borel hierarchy, it obtains an intermediate theory. And one can also go beyond the Borel sets, assuming some set theoretical hypothesis. And actually, if one is willing to drop the axiom of choice and work with the axiom of determinants, instead one can even get in contrast to the undecidability result, decidability for the full monadic theory of order. Something that could be mentioned as on the side here is that the Borel theory of topology, again, is equivalent to the monadic Borel theory of order and thus decidable by those arguments. But this is really specific to the one-dimensional line. If one uses even the R2, if one uses even R2, then one can code some geometry inside the theory, and it becomes easily undecidable. Okay. So let me shortly mention the reason why all those intermediate theories. Okay. Okay, I'll try. So let me come towards the reason why all those intermediate theories actually turn out to be the same. Namely, the proof requires not really all that we are talking about the Borel sets, but only to have a class of sets which satisfy the Baire property and are stable under some specific operations. We would at least to have the F sigma sets, because we use them to build all our canonical models of formulas. And we would also like everything to be somehow preserved by autohomeomorphisms of the real, or at least order automorphisms of the reals, which is essentially the same, because the theory cannot distinguish this. And actually, what will be important, the proof that we can check things locally on Cantor sets. So if we have a Cantor set in the reals and the complementary intervals, and the sets are nice, for example, Borel with respect to all those parts of partition, then we want them to be nice with respect to the entire thing for our proof to work. But those wide properties are satisfied by many classes, for example, the projective sets. And then we see that we even only need the Baire property for projective sets and not determinacy, which at least in set theoretical consistency strength is a much milder assumption. And actually, there also is a kind of largest class of sets for which this proof works. It's what is called the Baire property in the restricted sense. The set has this bare property in the restricted sense. If it has the bare property in all subsets of the reals, and it can actually be shown that it suffices to check this for Cantor sets. Yeah. Let me also mention that because the bare property holds for analytic sets, even in ZFC, we get undecidability. We get decidability for analytic sets, in contrast to the fact that under the axiom of constructibility, one level higher in the projective hierarchy, we will obtain undecidability by essentially simulating Shallard's proof in the setting, which only uses the well ordering of the reals, which can be found on the next level under those functions. Okay. So that's about the context of the proof and of the result. And next, I would like to talk about the proof of the result. So throughout, I will use an equivalent formulation of MSO, which is more convenient for us to talk about our notions. We will not quantify over subsets, but over labelings of our domain with finitely many labels, which could be phrased as maps to a finite set. And while in first order logic, one usually works with types, which are essentially theories with some added constant symbols, which satisfy the theory of some certain elements. Here for monadic logic, of course, we will need not to talk about first order constants, but about monadic constants. And and this again could be phrased by an additional labeling, which is added to our theory. And we will mostly talk about the types of some labelings, the reals. And then instead of quantifying over a new element, one can quantify over a refinement of the current labeling. And finally, I will often talk about when two subsets of an order embed into each other. And whenever I do this, I mean that we have an order preserving and label preserving injection. So much about notation. Now let's first see what Shalard already did in 1975 when he tried to prove originally the decidability of the full theory of the reals. The general idea is to use some induction on the quantifier prefix, and because quantifiers can no longer be contracted in monadic logic, one needs to use a generalized quantifier prefix, which allows to have several identical quantifiers in a row. So we do an induction on a number of quantifier alternations, but the size of the quantifier block may increase throughout the induction. More precisely, we can really define the stratification of formulas, which have quantifier blocks with first K1 existential quantifiers, then K2 universal quantifiers, then again K3 existential quantifiers, and so on, parameterized by a tuple of natural numbers. But this kind of boundedness is nonetheless important because it guarantees that for each fixed tuple K, we only have a finite amount of formulas up to logical equivalence, using that we are working in a relational language. And so, since every formula in contrast can be coded by some such formula, really our task of computing whether a formula is true just becomes the task of computing, given a tuple of natural numbers K, which formulas with quantifier prefix K are important. Okay, I should maybe also shortly mention that it's not quite a quantifier prefix because we need to also allow Boolean operations in between those quantifiers once the formula work. This is a minor point. And yeah, the main result we get with those restricted quantifiers is kind of compositionality result for theories, namely that if we can decompose a linear order as a lexicographic sum of some smaller linear orders, then we can compute the theory of the entire thing from the theory of the pieces, and we need to somehow know how those pieces xi fit together in the lexicographic sum of the xi, and this can be given by knowing the monadic theory of the index set labeled with the theories of the pieces. And the main examples this will be used in the proof is for decomposing an order into two parts, for decomposing an order into a countable sequence of order type of the natural numbers, or for decomposing the reals along a Cantor set, so giving the colors along the labels all along a Cantor set, and for each of the intervals in the complement of the thing, give also a theory of this interval. And then, in any case, we are interested where the sum becomes the reals, essentially. So that's until now we have only talked about the somehow formal setting of Shillard's proof, and the actual combinatorics comes in when we can reduce to so-called uniform labelings. So labeling is uniform if it looks the same on every open interval, and looks the same here needs to be phrased in terms of types because isomorphism would be too strong to expect it. So for a given quantifier prefix k, which is a tuple of natural numbers, we call a labeling k uniform if all open intervals have the same k type. This seems to be a rather strong property. For example, if one applies it to a partition into a countable set and its complement, then this will be uniform for any reasonable value of k, if and only if the set is either the countable set is either empty or dense. So in this case, it will actually be determined up to isomorphism. But nonetheless, we can obtain those uniform colorings in general. First, one can show by a compositionality argument that it suffices to check the condition for intervals with n points in a given dense set, say the rational numbers. And then by some Ramsey theoretic argument, one can see that actually everything is uniform on some interval and use this to get a rich supply of uniform intervals. Using this technique, Shillard reduced decidability, even in the reduced the theory of the monadic theory, even in a general non-Borel setting, to some very restricted kinds of quantifiers. One of those quantifiers asks for uniform refinements of a given labeling, and the other quantifier asks for Cantor subsets. And moreover, we then only need to answer questions on those Cantor subsets, and can assume that those Cantor subsets again are uniform labels. I didn't talk about the precise bound K for the uniformity here anymore because it's a bit technical, but all of this causes no problem in the proof. Okay, so what remains to understand is quantifiers over those uniform refinements and over uniform Cantor sets. And actually turns out that the combinatorics, both in the classical setting and also the Borel setting, happens essentially with the Cantor set quantifiers. In the non-Borel setting, those uniform Cantor sets are still somehow rigid enough to code many things that ultimately yield undecidability. But in the Borel setting, we know that many Cantor sets exist by some results of Borel sets. And in particular, if a type of a Cantor set is not realized, then in the set with the bare property, we will actually be able to find a bare category obstruction for this, which can be described effectively, and so obtain decidability. And as a maybe easy example of those techniques, let me show a concrete result that can be proven using these tools, namely a definition of the class of meager sets in the Borel monadic theory of order. And it's actually not clear to me whether a similar definition works in the non-Borel setting. So this really is something which we can do using the bare property. So a Borel subset A is meager if the following property, which crucially is expressible in the monadic theory relatively straightforwardly, holds on every non-empty open subset U. So everywhere we have the property that we find some Borel subset B, which is dense, but which on every Cantor subset C, which does only meet this thing, and our small set A, we have that B cannot be dense in C. So How can one prove this? First, let's assume that our given definition here holds, and we want to show that A is meager, so assume that A is not meager. By the bare property, we know that A is co-meager on some open subset. Since we have everything restricted to an open subset in this definition, we can restrict to a case where A is co-meager. And now we would be given a dense Borel subset B and want to show that there is a Cantor set C, which is included in this co-meager set, together with the dense Borel set, such that B is also dense in this Cantor set, and this is a straightforward variation of the usual construction of Cantor sets. But in the other direction, we will use the bare category extraction, so we should check something on every open subset, but let's just check it on the reals, because it's essentially equivalent. And let's look at our meager set. This is included in the meager F sigma set, which so a union of some closed sets AN with empty interior. And then as our set B, we can actually take any countable dense subset which avoids this meager set on this larger F sigma set A. So let's assume we have a Cantor set C, which is included in A union B. So B is countable in C, and C is contained in all those countably many sets. So A needs to be non-meager in C, and thus some AN needs to be non-meager in C. But AN is closed, and the closed set, which is not meager, needs to have non-empty interior. So actually, AN has non-empty interior inside C. And since AN is disjoint from B, this contradicts the fact that B is dense in C. Okay. So this explains why we see meagerness in the theory, and now let's go on to actually use the bare category methods. So by Shelar, we know that every partial type can be built using those uniform types, binary lexicographic sums, and product with the natural numbers. This is what was used to show the restriction kind of quantifiers I mentioned before. And for uniform Borel types, we will need only one additional operation to generate all types of Borel subsets, which somehow shuffles Cantor sets densely inside the reals. So we start with a labeling of the P of the Cantor set and a labeling Q of the reals, which should be thought of the label as the labeling on the combinatorial intervals, and a co-meager color sigma 0, which will label which will turn out to be the co-meager label, and this we call sigma 0 here. And the idea is that we embed the Cantor set into the reals. This gives us also already the labeling on a Cantor set, so a small piece of the reals. Now we look on each interval, the complement of this Cantor set, and we repeat embedding this Cantor set in there. Of course, after each finite step, we will still just have a Cantor set, but if we repeat this countably often, then we will produce a countable dense union of Cantor sets. This will still be meager, and the complement will be labeled with the co-meager label sigma naught. And the completeness really depends on the bare property, because we will have a co-meager label here, and expecting it something like this holds will only work assuming the bare property. Namely, let me mention why we will have this always with Borel sets. Namely, if we have a Borel labeling, every label is meager, or somewhere co-meager by the bare property, as I mentioned. So if we stick to uniform labelings by those methods, then our label will be either meager or everywhere co-meager, because we know that being co-meager is definable in the theory and doesn't need to be the same on every interval. And so there will be a unique co-meager label. Of course, there can't be two by topology. So, and this will help us in answering the main question we actually need to answer, namely, giving a labeling of the Cantor set, can we embed this labeling of Cantor set with this labeling into the reals with our given labeling? If, namely, this labeling of the Cantor set again will have a unique co-meager label, this could be different than our given one. If it's the same, then we can essentially always construct the countersets which we want to construct, unless there are some trivial obstructions like some label not occurring at all or so. But if they have different co-meager labels, then the bare category obstructions we already saw in the proof of meagerness may apply. But this then can be computed because those are the only obstructions. Okay, so that's all I wanted to say about the proof. So maybe let's next pass to a few related questions. And the first one is that there are two natural formulations of the Borel monadic theory. One is the Borel monadic theory of order we discussed before, but there is also a more expressive one, the Borel monadic theory of the binary tree. Here, for example, one could take all finite or omega sequences of zeros at once, regard this as the somewhat infinite binary tree, but also with elements for all branches, and equip it with the prefix relation and say the lexicographic order, although the latter one is not important for decidability purposes actually. And then, well, the monadic theory of order will just be the restriction of this to the subset of branches, because I mentioned that the monadic theory of order of the reals or the Cantor set with the lexicographic ordering is essentially the same. And in contrast, the restriction to just the finite nodes, which is S to S, and this has been shown decidable using tree automata by Rabin. And so this new theory here would be the natural combination of those two theories, and Szilard also asked about the decidability of this when he asked about the decidability of the monadic theory of order. Let me also mention why the new theory really is more expressive than the old one. Namely, we can now express Borel determinacy as a sentence in this new theory. This is rather straightforward. But the theory of order works only using the bare property, so it works under some much weaker assumptions. And now it one uses some, for example, results that Borel determinacy needs a large fragment of zeta C to be proven, or if one passes to projective sets and tries to do the same, one sees that really there are cases in which the monadics, in which my algorithm for the theory of order would still work, but Borel determinacy fails, and so the natural approach to this theory could not work. But we still hope that its theory might have an automata model, and the ongoing joint work with Mikołaj Borańczyk, Antonio Casares, and Paweł Paweł is improving this. Finally, I come to a slightly unfortunate thing I have to mention. Last week, I found a gap in the proof of a lemma for the decidability of the monadic theory of order. This does not seem to yield a counterexample to this lemma in any way, and even if this lemma were wrong, the fragment of the logic which causes the undecidability in the non-Borel case is not affected by this fragment, so I'm still rather optimistic that this gap can be fixed, but I couldn't do it over the last week. And for example, even if this gap could be fixed, it may still be that the bare property alone is no longer sufficient for this, but we maybe need a bit more determinacy or so. And in this case, of course, some of the strengthened results, like that we get decidability for analytic results in ZFC, might still be affected by this. Okay. So here are some of the main references I mentioned. It's also the preprint of October, where I found this error.